All right, let's get this started. Let me get out of studio mode in OBS. We're not gonna do any fancy camera changes or anything like that. Oh. Hello, folks. How's it going? Who's in today? I can't really see who the viewers are, so just say hi. Gonna edit the stream info. This will be number 5. Starting a programming language, number 5. Cool. Share it on Twitter. Share it on other places. Cool. So I'm running really low on energy today. Just a long day. The weather is crap over here in Stockholm right now, so that hasn't helped either. And I guess the camera might be a little too far. There you go. So yeah, let's make the best of it. Quick recap. We are building this language here, a language that I was sort of joking about earlier this year, that should have the type safety of a camel, right? So only a subset of all the possible programs that you can write are validated and marked as safe and will pass a compiler. So it has an expressive type system that is super safe, which is really nice to use. And we like the scalability of Erlang, so definitely an actor style or a virtual machine that supports some form of green threading or fibers with mailboxes, or just going full in on actors, right? But the kind of runtime where you can build. Yes. Hello, Antonio. How's it going? Good to see you around here. The kind of virtual machine that would allow us to build something that, if it fails, right, it can self-repair to some degree. But we also like the language to be expressive, right? And to that intent, having a macro system that allows you to build more expressivity into the language to solve certain problems will be fun. We'll see how that goes. But this will be something that we would like to take from Racket. And there's, of course, tons to be explored here. But yeah. Lastly, we would like a language that has the kind of developer experience that you can see in Rust. So a DX that sort of cares or gives a crap about you as a developer, right? Programmer. And it shows. And we forgot after that tweet, or to include in that tweet, right? To mention the kind of tooling that you can get from Faro. And I think it's fun to go back to one talk here by Deech. Where are you? Here. Called What FP Can Learn from Smalltalk. I'm going to pause this. There. All right, play. So you can see something. Yes, and this is an amazing talk by Aditya Siram, Deech on Twitter, where you can see the sort of things that you can build within Faro, right? To understand what the hell is your code doing, right? How the hell is your system running? Stuff like that. It's pretty amazing. Like, I wish I had most of the things that he's mentioning here in one way or another, so that I would be able to, for example, justify certain technical decisions by getting hard data on the state of a code base and so on, without necessarily having to sit down and say, well, I'm going to build this custom parser, right, for the entire code base, built on top of some programming language parser, right, to extract some information about it. And to be able to do this not just with the static side of our code, but also with the runtime aspects of it, right? So there are some bits of the conversation here where he's plotting, I think it's around here, the number of instances. I think this is the number of instances of a particular class of object to see how that would impact garbage collection, which is interesting. It's not something that you can as easily do in other languages. In Erlang, you could do something like this, right? You have some tools for introspection of the actual virtual machine, but since it doesn't have a graphical environment in the same kind as Faro does, right? Then it's not as straightforward to just say, well, I'm just going to open a REPL in Erlang, right? Or Elixir even, connect to a running VM, right? And then just start plotting these things out intuitively. Yeah, so that's what we started building. Along the, I think a couple of weeks ago, Camille also mentioned to have the portability of JavaScript. But I took that as a sort of spin on just have it compiled to WebAssembly. So that's another thing that we're considering here. Right? So yeah, we're playing around building a language that fits this criteria. And we're starting very small. The language we built so far, you can see in this repo, it's called QLang in Abstract Machines. I'll drop a link to this thing. And this is just an experiment. We're not really here trying to build a production-ready language that people can use. Right now, we're just playing around with all these topics, all these constraints, and seeing how they fit together. Because there's some tension between them, right? Like the fact that we want to have expressivity at the macro level, allow people to extend the language, right? But also allow people to be able to introspect the language in certain ways to understand what the code bases are doing or are not doing, right? That will bring some challenges up. All right, so going back to the captain's log. So far, this is the things we've been doing, starting on August 17th, 18th, 22nd, 24th, and now on the 29th. On the last stream, we actually made Q Turing complete, which is great. We added support for a couple of things, like multiple function clauses, right? So if I open a little frame here, here's a little bit of Q. We don't really have syntax highlighting yet, so I'm using OCamls. But you can, for example, add new clauses to foo to say, well, if you call it with 2 arguments, you go there. If you call it with 1 argument, you go here, right? We don't have very well-defined rules for actually validating this shit. This is just parsing at this point, from what I'm reading in the log, right? We also have a pattern matching, but this is really variable binding right now. We're not really going for full-on structural pattern matching or even deconstruction of values, right? But we have started support in the sort of parsing toolchain to add more kinds of patterns and be able to support them later on at different stages of compilation and also runtime. So that's one thing we have there. And then we started playing around with an interpreter to be able to do a hello world. And in this tiny interpreter, we just set up an environment, right? And the environment, there you go. The environment is just a collection of scopes, right? That form a singly linked list, I guess, where every scope can point to its parent. So this gives us things like, shadowing for free and lexical scoping for free. There's definitely edge cases we have not considered while implementing this, right? But you make an environment, you bind something. If you make an environment, like if you push a new scope in there, like an inner scope, then you have access to your outer scope, right? But the outer scope doesn't have access to the inner scope. The inner scope will become, the outer scope will become the current scope after we pop the current scope. So you're sort of traversing that list by pushing and popping from it. So when you pop something, because a scope is dead, then all the things in it are gone. And that seemed to work so far well for our use case. It wasn't much, but it was fun building. And that way we actually go to our tiny like interpreter, and this is just like an ASD walking interpreter, right? We get a module, and a module is right now a piece of our parse tree, our ASD the ASD that we build by consuming tokens from source code, right, through Elixir. And here we're just eventually calling a specific function, like an entry point function that needs to be defined for this. And we just evaluate everything every time. And we have a special case here for a function called print. So we will need to pay attention to some of the FFI, right? And how to build that interface so that the platform can provide certain things for the language. So the VM, eventually will have to go down and say, hey, operating system, please print this thing, right? Which we don't have right now. So what we did was just say, well, if you are about to make a call, right, and the ID you're calling to is the print function, right, then we will just grab all the arguments, evaluate those, and use Rust prints, right, a print macro. So that way we actually get something out. Yeah, so that was the little interpreter we did. And with this little thing, we managed to get a hello world. So if I do cargo run, main queue, this should say hello world at the end. There you go. It is still doing like a debug print of the whole literal string, but that's sort of what print is doing, right? Just using this. That was okay for them. Anyway, so after that, today, or the things we had for today, were these two, right? First one is figure out how to skip ahead when you get a parse error. So we can do incremental parsing of a file to continue sort of, giving you good feedback on that file and not failing on the first error. Because right now when we start doing that, then eventually we just get a lot of weird errors. So I think at some point we will want to start a test suite for some of these things. But let's say if you're missing like a brace here, when you do try to run the program, right, then the first error you get, it's like, okay, that tracks. This makes sense. So this is saying that, where we have the name for this value declaration, we actually expected a value because we're expecting values to go one after the other, right, within a single set of braces. But then everything else that we have here is just kind of garbage, right? It's just saying, oh, we found an equals, great. Parentheses left, great, right? Whereas what we would like to do is say, okay, if we actually have an error there, maybe we'll just backtrack, right? Mark that spot as an error and just continue parsing. So this will just show that. So that's one of the things that we could do today. The other thing would be to begin a macro expansion phase, right, in the sort of compilation chain. Read the file, get the tokens, grab those tokens, parse them into a parse tree, right, and then run a macro expander there. And one of the reasons we did the tiny interpreter was that we would want to actually have the same sort of emulator or the same interpreter really, both for the code that will evaluate at the macro level and the code that will run. Now, this doesn't necessarily mean that the code will be ASD walked, right, when you want to run your program. So we have some things to talk about, I guess, there. But it would mean that you can use the same language, right, for defining both things. And that could be great, and that could be horrible. Depends on your views on macros. Because, yes, you would be able to build Turing complete macros, which sounds like a horrible thing, but, There's things like TypeScript out there. You get a Turing complete type system. Is it really that bad to have a Turing complete macro system? Maybe, maybe not. Anyways, so to do that, I was considering actually starting a tiny VM. Why? Because right now we're in that process where we go from like the source, right, to tokens, to a parse tree, right? And we're sort of evaluating this thing. But I know that I don't want to have this interpreter right now or later, right, for evaluating the actual code. I want to be able to grab that parse tree, right, lower it down to something smaller, turn that into something that's more efficient to run, right? Ideally, some form of like packed instructions, right? Something that we can put in an array, a vector somewhere, and have a CPU efficiently use, right? So I'm wondering if, or how rather, this will fit into the macro expander. So I was reading this book, Lisp System Implementation. Is it Lisp System Implementation? But Niels. Oh, it's not there anymore. Yikes. There, this one. And if I'm not mistaken, so there is a really interesting part or a diagram. Maybe we'll be able to find it. Maybe not. I don't think I have a PDF version of this though. But there is a diagram that shows how, at some point you have the tree and you want to evaluate that tree, right? So what you do is you actually compile that thing, right, into something that will run on the VM, and then you just run the VM. And the output of that program is actually more tokens that you put back in. So you have this like tinier incremental, not really incremental, but like a tinier build that is just building the macro stuff, right? And executing that in the exact same way that you would be building and executing your code for your program, right? So I think maybe that grants us a little drawing. So if you give me a sec, I'll get the iPad set up. I didn't do that. And maybe it'll be easier to do that drawing there. And we're back. Oof, 9% battery. No bueno. Okay. So opening this thing over here, closing Discord, closing all the stuffs. Cool. First I'm gonna plug that in here. And I think I'll have to open something like QuickTime so you can see it real time. Okay. Ah, there you go. QuickTime is even popping up. See here? Operation could now be completed. Alright, QuickTime. Movie recording. And we're gonna pick iPad. I cannot see iPad. Huh. Why can't I see you, iPad? Hey, Hika. Nice to see you around here, man. Yeah, it is on an open repo. I just dropped the link in the chat. Okay, so let me just restart the iPad. Let's see how we do this. Light the power off. Great. Powering back up. Cool. Trying to unlock this thing. All right, let's try again. Maybe I will close this. Quick time. Ooh, can't really type anything. Close this stuff. File, new movie. And here we have iPad. Excellent. There you go. That's the stuff. Cool. So, sort of what I was trying to say, right, is that, yeah, I guess we have this part of the drawing there from, okay, never mind. I'll just start over. We have some sources. We've got some sources right here. So, hello. Color. This thing is not responding. Is the pencil dead? No, 70%. All of the technical issues, there you go. Why weren't you working before? Okay, so we got some sources, right? And these files will end up being sort of tokenized. So we'll have a lecture here in the middle, and this little box is gonna like read lines, right, of text, and speed out tokens. And sort of at this point we have like A, B, C, right? Semicolon, all of these characters. At this level, we actually have little pieces of data that are much easier to work with, such as an ID, for example, right? And this is like some kind of text, or essentially an equal sign, right? As a piece of data, sort of distinct from the character itself that we're using. And this thing would have to go into the parser, right? And from there, we will actually apply more rules, right? And either we get out with some errors, like diagnostics, such as this is invalid diagnostics, such as this is invalid syntax, right? So you could say, I'm gonna write a program, and let's see, I'm just gonna go for blue here, and say ID, right? Or let's say X equals 1, right? And this will be a string of text that once it goes through the tokenizer, it will become a series, like a vector of tokens of data structures where we have ID and we say X there, right? And then the next thing on that vector will be an equals, and then the next thing will be an actual number. So we'll have like a number here, and then we'll put 1 in there. So once we go through the lexing and we go into the parsing, in the parsing we're actually going to build, for example, an assignment expression. And this would be a data structure. And here we will have like the name of the variable, right? And this will be like ID X, right? And then we will have value. So note how the equal sort of is disappears. Is implied now by the fact that we have an assignment expression, right? And of course, we will have tons of kinds of expressions. So here, we would just say, okay, well, in this case, it will be like a number expression, or like a really would be a literal, right? So literal, and then number, and then we can put the number 1 there. Cool. So far so good. Now, why are we walking through this again? Because what we really want to figure out is, do we go from the parser, right, that emits a parse tree, right, into an interpreter, right, that evaluates parts of the program, right, and spits out more tokens for us to parse, right? Or do we actually go down through a compiler, right? So just entertain me for a second here. No, that's not the right word. Indulge me here. We go through a compiler, right? That eventually emits some bytecode that eventually is executed by some virtual machine, right? And this is the thing that emits more tokens, right? That we that then we parse, right? Again, and compile again, right? Until eventually you actually have the output of the compiler, the final output of the compiler, right? Which would be the final bytecode here. Final bytecode. Of course, in the middle here, we can add more layers, right? So we could say there will be some type checking happening after every parsing, so we can only build programs, even macro programs, right, that are safe under certain rules of safety, right? So in my head, I think a good diagram to aim for will look a little bit like this, right? We get our tree, our parse tree there, right? I'm gonna actually remove that. Yeah. And our parser gives us back our parse tree. Now we sort of need to grab every piece of code at this point that is part of the macro program, the compile time program, right? And compile that down to bytecode, right? So a part of that is going to be, we will have essentially a macro expander box here, but I will leave that aside for a second. We'll have a type checker, right, in the middle. So the programs that come out of this type checker would be the kind of parse trees that we want to be able to run, right? And for my lack of imagination, we'll call this a type tree, which is also what OCaml calls its typed representation, right? So this thing is something we would want to actually compile down to some bytecode, right? So I'm gonna put a box here, and I'm gonna call this compiler. This can have many other names. Could be a code generation stage. We could have several simplification layers in the middle, right? That translate the type tree into like other programs, other descriptions of programs that are completely equivalent, right? But are maybe easier to compute or easier to pack in bytecode for later execution. And the output of this thing is going to be some bytecode, right? Which is the thing that you would finally run. Okay, so far so good. If this was the normal sort of execution of the program, then this will be like the end state. The program will be the bytecode, right? So maybe we can do it there. We spit out some bytecode. Eventually, later on, right, that bytecode will be picked up and executed by the virtual machine. Virtual machine. She's fine. But for the macro part of the program, we want to be able to say, okay, we go through the parser, we go through the type checker, we compile it, we get some bytecode, and we actually go straight into the VM, right? And we execute that part of the program that should be executed at compile time. The output of that program and this is something that we can try to enforce with the type checker, right, will actually be more of the parse tree, more tokens, or maybe even more actual parse tree nodes, right? But it definitely will be more code, right? So we speed out code. So in that sense, you write a program, right? All the way above here. And the first compilation pass, we can maybe put some numbers here. So I'm going to go for pink there. The first compilation pass is actually going to come down here and say 3, right? We're going to parse the program. We're going to type check that, right? We're going to actually get an executable version of that, something that we know how to run, right? And then we're going to actually run it. And the output of that program we expect to be code, more code, right? So 7. But this doesn't mean that your program is going to run, not like all of your application. If you start a web server, then, you wouldn't be able to do much there. But this will be enough for us to be able to sort of compute parts of, or actually the entire macro expressions using the exact same language and the exact same runtime environment that we want to use later on. So we go 1, 2, 3, 4, 5, 6, 7, right? Eventually we go back into the parser, right? And this may be back right into the type checker depending on what we choose to speed out in the first pass, right? If we speed out tokens, then we go back into the parser. If we speed out parts of the tree that we expect to be valid, right? We probably will still want to have some validation of that before we go into type checking, but let's say you can only construct valid things, then we will still go into the type checker to make sure it is typed. And from there, we'll just go 9, right? Type check the final program that you want, right? Actually compile that down to bytecode and then use that bytecode to run the application. So that will be a little bit of what we were trying to do. Oof. So I'm wondering, right? Does it make sense to start with this tiny VM, right? And just go from, let me pick a different color here, and just go from 3, where we are right now, right, straight into 6, just so that we can, we definitely will need something in the middle, at least number 5, right? So we go 3, 5, right, 6, 7, and we can repeat that if we need to. If we make code, right, that creates more macros or whatever, then we can continue to do that. If we don't, then the moment this program finishes executing, right, then we'll have the final version of our program, which means we can just go 3, 5, 6, 7, and then go to 8, right, and then go to 10, right, and then go to 11, and that should run. And the VM should be pretty much the same, plus minus some host things, right? Because we might not want the macro system to be able to do certain things, right, like arbitrary I/O. I think it would be reasonable for it not to do arbitrary I/O. Or maybe not. Maybe it's fine. Ooh. Cool. I think I'm going to try to take a screenshot of this. Oh no. Okay, there we go. That should work. Cool. Save. Cool. The alternative diagram here will be just to cut from the parser without a type checker, without the compiler, without a VM, right? And just have the AST walk interpreter, the one we currently have, right? Just expand into more code. On the one side, that would mean we can test the macro system right now. I mean, not right now, but we still need to build this pipeline, right? Because right now it's pretty manual. But it would allow us to say, okay, if you prefix something in the language, and by the way, this is something we haven't talked about, right? But like right now, you say I'm gonna have a function, so x equals, right? And then you just put arguments, right? With the bodies, and then you can put more clauses like that. But how do we tell the program this thing that you have here is actually a compile time function? And do we do that? Maybe we don't. Maybe everything is available at compile time, right? But I mean, when I say everything, I don't mean everything. Like your program may not run at compile time. But we will need to have a nice way of saying, oh, this is something you cannot do at compile time. I wonder how arbitrary that line will look. Let's say that your function is not just any x, you actually have like a listen on a server, right? And then in a macro, you want to be able to sort of execute this function. If you were able to do that, then your program will just never finish compiling, and that sounds terrible. It will just open a socket, right, and do some arbitrary I/O, and then you might as well, yeah. That sounds terrible. I would not want that to happen. So we'll have to find a way of saying, hey, this is something that I would like to have evaluated at compile time, right? Even if it's not. Okay, so maybe even mark something as a compile time function, right? Like this thing that we're about to define is not just listen, like body definition. It's, for example, macro, right? Macro, listen, and then the body definition, right? Or I like also how I think SIG does it, right? Where they say comp time. At compilation time, this function is available. Now there's 1,000 ways that we can try to define this. We could define it as a keyword. We don't actually have any keywords just yet, so we could start adding some of that. We could also define it as a convention in the language, like for example, anything that starts with at, like you would see in Elixir sometimes, right? That'll be a thing. Hello. Okay, so could also be an attribute, right? If we were to add attributes to different things that we can parse. So if you say like at, right, macro, and then just a constant function, not very useful. And then we would know that you're calling a macro because we know that the thing you're calling is a macro on its own, right? Rather than you having to be specific about how you want a certain thing to be called. So what do you think? Which one should we go for? On the one side, we got the VM and versus the interpreter, and on the other side, we have sort of this implicit definition and evaluation of what is a macro versus an explicit one. The explicit one, we can figure out whether we do that explicit at call time, right, or at definition time, right? Either you try to call something and say, I would like this to be called at compilation time, or you call something and that something says, I am a compile time function, so inherently it will be called only at compile time and then removed. So I guess we have three choices, right? First one, VM versus interpreter. Second one, implicit versus explicit compilation time. And the third one is compilation time at call site or at definition site. What do you think? I'm going to write them down here. VM versus... Wait, that's terrible. There's a chat somewhere in there. Just let me know what you think will be more interesting to play around with, and we'll get started. I reckon we have another 45 minutes, an hour to play tonight. So I feel like going for the VM and explicit and actually doing call site um, markings of something being a macro. And the reason is that I would like to be able to evaluate as much code as I can at compile time, as sort of maybe even a program optimization, right? Like if I have some things that I have the data for already, then I will just try to call them at compilation time if I don't need them to be executed more than once. So then I pay the cost up front and off we go. The program should be faster, I guess. Um, and yeah, and that's inherently an explicit path here. And the VM, because I wouldn't like to have to redo the work or have two different evaluation form. I guess not necessarily semantics, but two different interpreters, right, for the same language. I think it'll be fine if for other bigger languages that have I don't know standards like Ruby or just massive communities like Python, right? But right now, the least code I write for this, the better. So I think the VM could actually give us a good kick. Good return over whatever time we put into it. Hmm. So I have been looking around at how other VMs have been built, just to keep sort of the space fresh. This one in particular was interesting. Yes. So Lua went from a stack machine to a register machine, right? When they moved from Lua 4 to Lua 5. And because I have prior experience building something that is register based, I figured, okay, and we could probably do a register machine here as well. There's also less tutorials and documentation and just stuff written about register machines. Most of the things you can find around when you're looking for, okay, how do you build a virtual machine? They go for stack machines. And I was looking actually at some Erlang code here to see this here is the output of the compilation process. This is the thing that will be encoded, right? That you can read out. The virtual machine will read up to execute your program, or rather, this is the thing that defines a module, right, and so on. And the functions, your program itself, are here. So I thought it'd be interesting to play around with this a little bit and say, okay, we have a program, right, and we can translate from Q to Erlang pretty straightforward. And see what the output is, right? And start to get a mental model of how would the VM need to look like, right? For us to evaluate this. I think the iPad got locked. No. Unlock yourself. Okay. There it is. Just gonna have to tell it not to lock itself anymore. Auto lock. Oh, right, I'm in low power mode. Battery. Nope. Don't be low power. Be high power. There we go. Never. Cool. That works. So if we go into the Q program that we had written here, the thing that we tried to run, right? Um, Qlang, and then we said main Q, right? This thing. This will roughly translate to, let's say, I mean, we need a module name, so I'm just going to use A there. And we're going to have a function called foo, and that will take 2 arguments, and a function called main that will take 1 argument, right? So we'll get foo, and we're explicitly ignoring the second argument here, and we're going for the equivalent of print, which in Erlang would be format like that, and we'll just pass A in there, right? And then we'll have main with our arguments, right? And we're sort of duplicating that when we say foo and then say args. So we will see, okay, amazing. We will see what this compiles to, right? And start sort of working that virtual machine out backwards. Like, no, sorry, reverse engineering, I guess is the right way of saying this. All right, so we got our function main, right? So right here, we have a definition of a function. This is an instruction that we're sort of giving the virtual machine, like, please define this function. And it has some, it has some arguments, right? The name has the arity, the number of arguments it takes. And I think 4 is the name of the label. So the part of the bytecode that defines the body of this function begins at the label 4. So you'll see here we have label 4, right? And the things after the label are associated with the label. So if you set label 2, then when you tell the machine, please go to this label and start executing things, right? Then it just says, well, when I was reconstructing or reading this bytecode, I built a piece of data somewhere that said this is the second label, so these are all the instructions that followed it, right? Until I found a different instruction that set up and sort of broke that current line of execution. In this case, it will be function, I believe. Okay, so in that case, we have main. When you call main, it's gonna start executing at label 4, right? Ooh, that's nice. We can actually see hex. No, okay, these are just numbers. Never mind. Yeah. And here we do a couple of things, right? We are moving a value, and by move, I think we can say copy here. I don't know if this will be referencing the same value from both places, or if this is actually duplicating the value. Since in Erlang you can't, for the most part, right, terms are immutable, then you would expect this maybe to not automatically duplicate things. But maybe it does. Don't know from looking at this, right? Like, this doesn't specify that. And then we have an instruction that's called call only, right? Okay, so just sketching some things out. We will definitely have sort of some operations, right, that we want to do. We have move here, right? We want to be able to move memory across these different registries, right? Now, the way that Erlang works, or the Erlang VM works, and Dima, if you're around, so I don't know if you are, but if you are, then yeah, if I'm saying something here that's off, please correct me. It has sort of 2 rows of registries, right? You have the X registries, and we might see some Y registries somewhere, maybe not here. So in this case, this will be used as, inputs to a function, so function arguments. So we have that move instruction there, and this can have 2 things, right? And then I guess we could, like, naively right now model that as saying, okay, you got move, right? and then you're moving from some register A, right, to some register B. And you could say source and I think test, not revisitor, register. There you go. That'd be good. And then we have an instruction for calling a function here. And I don't know what exactly this means. Because we have the number f. Okay, where the hell is f? F2. I don't actually see f anywhere, right? I would have expected to see the name of the function, but maybe this is the label, right? I just don't know where f comes from here. I don't see that. So one of these will be the label, and the other one will be the number of arguments that we're passing in. So I reckon that if we were to say args, right, and just ignore that, then one of those two numbers will go from 2 to 3. There you go. This one went from 2 to 3, so this is the number of arguments that we're actually passing. And 2 here, I assume, would be the label. We can check that by actually just moving this thing around, right? So if we define it afterwards, then I would expect the label to be just called differently, right? Here. So the label now is 4. It used to be label 2. And when we did call only, we had f here and the number of the label, which used to be 2 and now it's 4. Okay, so we can more or less tell that this instruction here will actually take the label that we're about to jump to, right? And the number of arguments, right, that we're going to be passing on. So again, I'm not saying we're not really going to build the exact same bytecode as the Erlang VM, but I think it will be useful to start drafting something that sort of looks at it, since we want to have some qualities of that virtual machine, right, in ours. So we'll do call, and we're saying label, and we want to go strictly to a label. That will be like a number, and then we have like arg count. It might be that we define this to be much more differently, right? Instead of saying what the argument count is, maybe we actually pass in the references to the registers that we want to be using instead, right? But it just gives us an idea of what that is like. Okay, so at some point we will jump essentially to this label. And here we have a couple of interesting things, right? We have a test of a heap. 2, 1. This, of course, doesn't tell us much. And then we're trying to put the list, or use the instruction put list, right, to create part of a list, or to create a list. And I'm going to go ahead and venture that this is head, tail, and this is the registry where it should be put. We're going to confirm that soon. Yes. So if I grab this thing and just put like hello world A at the end. Cool. Yeah. So you'll see we're building this list backwards, right? Hello world happens at the end. Hello happens last, right? Which means it will be the head of whatever list had already been placed in there. Or this tail, right? So head, tail. This tail was actually built here by saying we're going to cons, right? Put the world atom in front of whatever's currently on the register X0, and then we're going to put all of that on the same register. And whatever was on that register as actually was built in here by saying we're going to grab whatever it currently is on X0, right? And we are going to sort of put that as a head of nil, which is the empty list, and that will be saved in this register. So this way we're saying, grab whatever we have in that register, turn it into a list, right? And then put on front the atom world, put on front the atom hello, right? but we are actually saving this on this register, X1. There is something happening here in the compiler where the compiler is figuring out, okay, what register are we going to use next, right? And you definitely want to keep these things packed as closely together so the CPU will have an easier time loading those, right? Rather than saying, oh, well, just keep adding at the end of the registers, because then you might need register 0 and then register 50, right? But if you need 0, 1, 2, 3, 4 in that order, then the CPU can sort of say, well, I'm just grabbing 0, but also just, grabbing 1 will be straightforward because they're close by, right? We know exactly what to keep loading into the cache there. It may actually read more. It might read like 4, 8, 30 of these registers at a time, even if it's going to use just the first one, right? So it's convenient to pack them that way. Then we're just moving a literal, and we saw that before, right? But it turns out that you actually can't specify literals that you want to move into something. So maybe our instruction moving from register to register doesn't make that much sense. Maybe this actually is like a value, like a literal or register, right? So we'll keep that there. Later on, we can figure out how we want to lay out these operations, right? Like something tells me we will want eventually everything to just be like a big vec of bytes, right? And you read one of those and you turn it into an opcode, right? Which will be like only move, not just move with all the stuff, just move. So then if you see that, you can request, okay, I know that we're a move, so give me the next U8, right? Or the next two U8s, and we will parse that and literally parse that, right? And treat that as a register or a literal and so on. But I don't know, maybe it's okay for us to put a lot of this domain logic, right, onto the actual representation of this data, and Rust has some tools to help us make sure that it gets pretty tightly packed. Cool. And then we have this other expression, hear me out here, instruction, right? That is trying to say, I'm going to call a function that's external. And I guess only happens when you call something at the end of a function. We can verify that as well. Like if I just say, all right, okay, here, right? Then the main function, yeah, now we're using call instead of call only. We are using allocate and deallocate, interesting, and we have a return here as well, right, as an instruction. So this is changing quite a bit. And if we don't have that okay, then we have call only, which may be a sort of a meta instruction, something that does both. Okay, I'm going to allocate this thing, I'm going to call that function, come back, deallocate, and then return whatever was returned by that function, right? Like a convenience to make the bytecode smaller. And here we have call external only. And here we have an external function, and we have a module, a name, and I assume this will be the arity, how many arguments that function is expected to have. Because if we do a third argument here, okay, then maybe that will be 3. Yeah. This actually is the same number, both cases. Cool. All right, so one thing that this answers is how would our virtual machine actually help us implement functions, right, that need to be outside of our program. So for example, when we called print before, right, and this function was defined in the interpreter by just essentially special casing, right, this evaluation function to say, if you're about to call the print function, then we know exactly what to do. We don't need to delegate it to more code. We're just going to run this little bit of Rust code, right, which is not something we want to do right now. We want to be able to, at a lower level, say, hey, you're about to call some function, it's external, right? So that's interesting. How will we do that? Because in Erlang, you have this idea of an MFA, which is a triple of a module name, function name, and the arity, right? And you can use this to identify any individual function in your entire system, right? So literally anything on the beam will have that. So if you do something like IO format, right? And then you want to print hello world, that you're essentially saying, okay, I'm going to have a module, which is IO, right? I'm going to have a function, which is going to be format. And then I'm just going to call that module with that function, right? I'm going to pass some arguments. And this works because the runtime is actually grabbing these values, right? And more or less using them to figure out where exactly is the code. And it will use this number of arguments, right, to find the right implementation of the format function that has those arguments, right? And try to pattern match on all the cases until something works. And if it doesn't, and you can see that it won't if we actually pass in something differently here, right? Then we will get, actually, no, I think this is just a runtime error. But if we say like, okay, no. No, that's good in both cases. It must be a guard that you have. So we're trying to call it with the right number of arguments, but the wrong patterns, the wrong kind of values. So that particular implementation for the IO format function for 2 arguments will fail. We don't really have anything like that. We're not really saying here's a module system yet, right? So we'll have to figure out how to do that. For the time being, I think it will make sense to consider that maybe this call, right, that is clearly local, needs to have a non-local version, right? So we will have like a local call, so we know like, okay, in whatever current program we're running, the function that we want to execute already is here. So you just go to that location in memory and start executing there, versus, hey, we don't know where that is, right? Please figure out where it is and how to call it. External call. And I understand that local and external can maybe be confused for where will this run. It's like the opposite of local maybe would be like remote call, right? And that would mean that could mean that somebody else is executing this for us rather than, it just being run somewhere else in the code, outside of our program, within the same virtual machine, right? So we'll have to figure out how to model this nicely. At the end of the day, it looks like both of them are pretty similar, right? The only thing that changes is how we specify where that function is, so we can jump there. You can imagine a little table, right, that says, oh, if you give me one of this, then I will give you a U8 that will be a label, right? So then when you try to do that, then we know exactly what label to jump into. Yes. Okay, so we'll leave this a label for now. It might be possible for us to know ahead of time exactly what the labels for everything would be. I think this will depend on the constraints we have on the runtime system as well. If we want to be able to dynamically load and reload some of the code, right, then essentially without having to recompile the entire bytecode, right, then essentially this would be this indirection of having a table that points to the label would be necessary, right? So if we know where everything is at all times, and you can just ship one version of the code, and you can update by updating and recompiling everything, right? Then sure, then we will always know exactly what label everything points to, right? So while we're compiling, we can figure out that, so that when you need to execute it, you don't have to think, you just run, right? Jump to this label. All right, I'll do it. Just keep going, right? No thinking. My allergies are killing me here. Okay, so what else do we have here? We need a way of moving things around, right? We clearly will need some registers. So if we were to start structuring, like a VM, right? we will have some code. We'll figure out later how to turn this into the right array. We will have some registries, right? Registers. And right now I'm just gonna use a vec UI. Again, we may want to use Rust structs for this instead, right? Like register. So pub struct register, and we'll just use I forget. Is it like repr c? I think it's that way. So we can tell Rust, please, the way I lay this structure down in the code, in the text, is the way I would expect it to be on memory, right? So Rust doesn't do any optimizations or any magic there. So this will be pretty hand-tuned, which will be handful if we want to make sure that all the instructions have the same size, right? So they're easier to cache by a CPU. Okay. Something we had before that we could bring back. Actually, I think we shouldn't at this point, but we'll need an equivalent version of that, or a way of mapping that to registers will be the environment, right, that we spoke of. Because at the end of the day, when we're compiling, we're figuring out, oh, when you make this call to this function, then we expect the environment to be like this. So the registers will be mapped directly to things that we want to have access to, or that we need to have access to, because we already have all the code, right? But we would need some form of heap, right, to put some other data. So for example, in our program here, sorry, yeah, we might actually finish in just another 15 to 20 minutes. Got real tired all of a sudden. But for example, in this program, we don't have any piece of text, right? Any data that needs to be saved somewhere. But if we did, and assuming, for example, that we had something like hello world, or like you said, right? Or I don't know, maybe just that. Then we would expect this thing to pop up somewhere on the bytecode saying, hey, please save this string, right? And this string is likely going to live on a heap because we don't know how big it is. Like this could be a pretty long string, right? Could be an HTML template, for example, right? So in that sense, we would need to have some form of heap. And right now, again, I'm just gonna be like, all right, this is just a vector of bytes. We'll figure out how to work through that later. It is likely that this whole loop in this particular emulator, I think I like better the word emulator here, since we're emulating some machine one. I don't know, maybe I'm biased because Erlang does use the term emulator. Maybe we'll just stick to VM, right? The loop here would be a little bit like, let's say we have that like that, right? It will be a little bit like, all right, infinitely, just once you start, right? And we're gonna try to read a new opcode, a new one of this, right? From this vector. And again, we don't actually have to have such a raw piece of data structure here, right? We can have something higher level like bytecode, right? So we can say, all right, match bytecode. Actually, we can even just do like while let some, right? No, maybe we will end up. Okay, let's just go back to the loop for a second. Bytecode, let's say next instruction, right? Next instruction. And then here, depending on whether we have a move, right? Or something else like a call, we will do one thing or another, right? And it is in these little braces where the actual emulation of the machine that will execute the code, right? The bytecode that QLang got compiled down to would happen. So going back to the picture that we were drawing earlier, right? So at some point we have Q syntax. Where's the blue here? We got Q syntax here, right? On this node, we got Q. We have tokens of Q here. We got the Q parse tree here, right? And then through this process, eventually here, right, in the compile step, we get some bytecode. Now that bytecode represents exactly what we wanted to do, but it knows how to tell that thing to this particular virtual machine. And this is what we're looking at on the screen on the left, right? Let me undo those highlights for a second. I think it would be useful to have a new layer for highlights alone. Perfect. So then I can just do whatever, and then that layer is completely isolated. Nice. Cool. So in here, if we were trying to manually compile, right, some of this code, we would have some things, some moves, right? If we were trying to use like Erlang style compilation from Erlang source code to Erlang bytecode, then we would have a similar way of saying, okay, the main function, right, essentially it's a move and a call, right? That's what needs to happen at a low level. When you're saying foo arg arg, like a pirate, then in down the hood, what's happening is we're sort of moving, right? And then this will be like the first vector register, so R0, right? And then we're moving that value to R1. And then the next thing that happens is that we're just calling foo. So we would do something like call, right? And then we don't know, I mean, we haven't figured out yet where foo is or how to make the program find out automatically. But assuming that we actually can put an address in memory here for the code, we will say, all right, I want to put the line number here. So this would be like L1, right? That's where the function is defined. And this function takes 2 arguments, right? So then we know exactly how many arguments to read, right? When we try to call this function by jumping straight into here. So our call branch here would first say, oh, I'm going to read like our count, right? So bytecode, like next, and we can say, give me the next U8, right? You just want the number of the count of the arguments. And again, this is something that we could have done with Rust just by saying, I'm going to have the arg count here as part of the struct, right? But this will mean then that each one of these enums will have a different size, which might be a problem. We'll see. So once we do that, we know exactly how many arguments we need to move around, right? Or actually, how many arguments we will have to have on the next scope, right? Because these are the 2 arguments or 3 arguments that need to be preserved when we start calling the next thing. Which maybe we don't want to have. Maybe we just assume that you've done your homework. So when you're doing your calling call, right, then we expect the arguments to be there. Because the bytecode for the foo function will actually be something like call external, right? Or, let's say call external, print, right, R0. Assuming that this will be enough information to find print. Maybe we'll need to have more info here, right? And then this will be designed so that R0 already needs to have the right value. So whoever calls foo is going to say, well, whatever I need to pass in as an input, I'm going to put there, right? And so on. Okay, so not much of a conclusion, but definitely some exploration that this sounds like a reasonable path. Since we have a very small language right now, right? The only thing, if we go to a parse tree, that we can build right now is a module, right? Which is a file with items. The items themselves are these value declarations, right? And we're making room for other things later, like module attributes, such as, hey, enable debugging on here or stuff like that. Or maybe even module level macros, right? A macro that takes the entire module, so you can then process the entire module and do something like automated tracing of functions, right? So you say, okay, trace this module for me, please. Thank you. And every one of these value declarations, right, that are about items in a module, will have a name and an expression. And that's a little bit what we saw in our main QL file here. We're saying, okay, this is a value declaration, right? There's a name on the left, and there's an expression on the right. And the expressions we can have right now are variables. So you can use a variable, like we use a here, right? You can use literal strings. So yeah, we could say, okay, hello, as a string here. That will be valid. Q. We can have function calls, right? Such as, print a or foo argard. And then we can also have functions, function declarations, right? Or definitions, or lambdas, right? This effectively makes functions first class in our language. And functions in Q are defined as a collection of patterns and the body that corresponds to each collection of patterns. So these clauses, fun clause, right, says, well, I'll have some arguments, and this will be a collection of patterns, and if that collection of patterns is matched by the inputs to the function call, then this body, which is just an expression, should be evaluated, should be executed, right? Right now, the only pattern that we support is a binding, right? But in the future, we will definitely have more patterns here, but for literal patterns, but also for sort of deconstructing of like records and lists and tuples, right? So then you can support sort of control flow by pattern matching on each one of these function clauses. If it doesn't match the first clause, then we go to the second, and so on and so forth, which I find super, super powerful when writing Erlang and Elixir. And I miss on every other language I use. Cool. Okay. So this gives me a little bit of an idea. We would need move to be able to put things in the right register so that when we do call, those things exist there. We would need call to be able to go to those places, right? If we don't actually have to do anything else with the call, this may just become a jump, right? Saying, hey, just go to this label, right? We'll have to do a couple of things here, like figure out like how to. I guess we just need to define this bytecode struct, right? To see exactly what it will look like. And I assume that somewhere in here we will actually have a big vector of bytes. So we can just jump into the right spots there, right? And keep evaluating. Which probably means we'll have a pointer, right, to the current byte. So, for example, I don't know, instruction pointer. This may be larger than U8, though. We'll see. Which will be the thing that the bytecode will use to say, okay, I move on to the next thing that needs to run from where I am. Cool. So in the loop of the VM, assuming that you've already loaded everything, right? We will begin with an empty heap, or actually the heap may already have a size, right? We'll begin with a number of empty registers that have nothing in them, right? And we will start polling and say, okay, give me the first instruction or the next one. And then based on the instruction opcode, right, whether it's a move or a call or a jump, right, then what we'll do is just say, okay, give me the next number of bytes, right, that correspond to this particular operation. We'll do something with that. Maybe we change some registers. Maybe we change the heap, right? It may be that the registers behave a lot like the environment that we built for the interpreter, right? So every function call has its own set of registers, right? And we just keep pushing things in there. So you make a call and then we just say, okay, I'm gonna push. Oh, the camera died in an amazing spot too. Let me try to get that better. 1, 2, 3. Let's see if that works now. There, it goes back. Perfect. Yeah. So that way we don't have to think that much about allocating registers efficiently. But then we maybe have some other problems, like the thing will just, either we introduce an arbitrary stack size, right? So we keep this many number of register collections, right, that you can use, or we just let you kill the VM by running out of memory. In any case, I think this is just a trade-off. Do we handle this complexity? Going back to the image, right? Do we handle this complexity at the VM level, right? Somewhere here. Or do we want to handle that complexity earlier on? So for example, do we want to be able to write a function like f, right? That just calls itself. And have this run indefinitely without right? Without running out of memory. So if we do, then we may not want to deal with different sets of registers like that in a naive way. Like every call is just push another new set of registers, even if it will be empty in this case, right? Or maybe we have a specialized instruction, like we saw on the Erlang VM with call only instead of call. When we had something else happening here, comma, then we had the call, sure, but also, right, we had more things happening here, like allocation and deallocations and a return. So this would not be tail recursive. This one would, right? Let's see what happens if you do f and then you just call f in there. It's nice that the syntax is so symmetric for this thing. So we need to export that. So f0. Cool. Yeah, okay, so this is just call yourself. There's nothing else that's happening. I assume that if we did something like s, like an argument a, then it will not change at all. Be the same thing as well. Yeah. And if we wanted to build a data structure here, of course, this will this will eventually out of memory, right? The machine, yeah. Okay, so here we're actually using test heap to build something. To put into the tuple that lives there. I'm curious. Does test heap actually do any allocations or not? Anyways, so that's a little bit the direction we will be taking with QLang then. We will start working on the actual VM, right? Defining some of the minimal operations that we need to support this current language, right? And once we have that up and running, then we'll go back and implement the flow, right? that we saw here, where we begin at the source, go through the lexer, parser. We don't have type checker just yet, so we can just assume that that passes. Go into the compiler, immediately run the VM, get some code out, right? And go back into the parser so that we can have compile time macros that are written in the exact same language and that are evaluated by the exact same runtime as the final code would be. Okay. To me, that sounds like a plan. I think I'm going to call it a night. I am really tired. I don't think we can start building this right now just yet anyways. How are you folks doing? Everything all right over there? Yes. Okay. Let's do that. Thank you, folks. Have a good night. I'm going to call it off. On the next one, next stream, I think is going to happen on Wednesday. So not tomorrow, but day after, around the same time, 8 p.m. CET. We will definitely start fleshing out this VM more aggressively. Try to get enough of the bytecode to run the current hello world that we have, right? We might not have the compiler that goes from the parse tree down to the bytecode ready, right, through that stream. But we will definitely be able to just see the parse tree on the one side, handcraft the expected bytecode, right, run that bytecode, right, and see what the output is. So then we can try to bridge that by writing that compiler and then hook it up into the sort of macro expansion. Okay, folks. Have a good one. Take care.